I'm very excited to be here today to talk about some of our efforts in developing training recipes for building language models and particularly for reasoning in language models. Okay, so let me start. I want to argue that AI is here today, or we've seen all this progress in AI because of open scientific research and development that is happening in this area, and because we had access to fully open model. However, over time, we've seen a lot of research and development in this area is getting closed off. But what does that mean now? Does it mean that now we are done with scientific language modeling research and innovation? I would argue no. We need still to do a lot of research to understand the science of language models, to improve them, and also build their next generation. Also, we need to make a lot of advances to push language models beyond language, right? Like in science domains, language models for health, and move it beyond text. Also, we need to mitigate their biases and risk, use these language models in real world, obviously work on LM agents, improve their planning, reasoning, test time scaling, and also make them suitable for deployment and build efficient model. So with that, I want to argue to facilitate innovation and also accelerate the science of language models, we need these models to be fully open. We want them to be transparent. We have access to their data. We want them to be accessible and reproducible by researchers and developers. So at UW and AI2, this is our focus. We like to build an open ecosystem such that we can build language models from at different stages, from pre-training to post-training to mid-training, and also building agents. In particular, my team is leading two efforts called Open Language Model, OLMO, and Tulu, which is our open post-training recipes. I also want to highlight that this fully open ecosystem is only one piece of puzzle in this landscape of AI these days. Okay, so with this project OLMO, we like to develop, study, and advance language models. We want all our efforts to be fully open, documented, and reproducible. And with this, we like to empower the AI community and also inform the public about how AI works and so on. Okay, so in this talk, I'm gonna talk about three efforts that we've done to improve mostly reasoning in language models. And these three directions are mostly orthogonal. And I'm gonna talk about pre-training, post-training, and test time inference. And many of my slides are from my amazing students and team members who have worked on these projects. Okay, so in the past year or so, we have released and launched a bunch of models and toolkits that we encourage all of you to work and improve even. In pre-training, we have released OLMO 1 and 2, our mixture of expert version, and also our full pre-training data. For post-training, we have developed our training recipe on top of many open weight models, such as Llama, Qwen, and so on. And also, we've applied that to our fully open language model, OLMO. And also, we have all the toolkit, data, and so on publicly available. And most recently, we've continued working on test time scaling, which we have released a Swan, Open Scholar, and Self-Rag, which I'm going to very briefly talk about those three as well. Okay, so just a quick snapshot of where results are standing is in our latest release of OLMO 2, which we have released OLMO at 7 billion parameter and 13 billion parameter scale. The base model at the end of pre-training, it is on par, and some data sets better, a little bit worse on some data set, but on average on par with Llama 3 and Qwen 2.5, same as 13B. Importantly, we have used less number of training tokens, and we argue that OLMO 2 is on this Pareto optimal curve compared to many other kind of open weight models, like Qwen, Quen 2.5, Llama 3.1, and so on. So this curve shows the average performance versus the approximate pre-training flops. And as you see, those are kind of those two stars show where to stands. A snapshot of our post-training efforts. So most recently, we have developed our post-training recipe on top of the largest open weight model, which was Llama 405B. And I'm going to talk about how this process is being done in this talk. And I can show you that Tulu 3 405B now is on par or better than DeepSeek V3 and almost on par with GPT-4o, which is very impressive, showing that now we are getting a really good result compared to even proprietary models. Okay, so with that, I first want to start with post-training because a lot of our efforts on how to make these models able to reason starts from post-training or happens during the post-training. And I kind of we'll talk about how we develop Tulu along this process. Okay, so how do we build a modern large language model? So it is roughly going these two stages, pre-training and post-training. In pre-training, the models are trained with predicting the next token, where data usually comes from large scale data, mostly from the web. Okay, but the model that comes out of this stage is not ready to be used for a lot of applications. It is not safe. It's probably not able to follow human instructions, and it's not that good at reasoning. When post-training happens, now models can do a lot of things. It can chat, it follows instructions, you can integrate it with tool use, it's able to reason, it's able to tell you when it is harmful, when it doesn't kind of follow the instruction, and so on. Okay, so we do post-training to align with human preferences. You've seen it in like when, for example, you use ChatGPT, which of these two responses you prefer. And like we collect this type of data to say which of these outcomes are more aligned with humans. We do post-training to be able to do tool use, searching, code execution, and so on. And also we do a lot in post-training for models to be able to reason. For example, in this case, we want to teach the model how to kind of solve this arithmetic word problem. Okay, so how does it work? Following many standard language modeling or machine learning pipelines, it requires these pieces. The data that we need to train on, a training kind of architecture and neural network, which in almost all cases, it's a transformer-based architecture, and a very thorough evaluation loop to tell us where we are improving, where things are not going so well, okay? And I'm going to talk about these are the three integral parts in building a very modern, successful language model: data, models, and algorithms. And during this talk, I'm going to talk about what type of data is important and what type of algorithms are useful for which type of data. Okay, so data plays a really important role in building these post-trained models and like pre-trained model. It comes from different sources in many different forms, and they are targeting diverse capabilities, right? So for example, we need data to be able to solve math word problems. We need data to build agents. We need data to kind of tell the model when it is not safe to respond to a query. But we need to design and use different algorithms on deciding when to use the right data and which of these algorithms are useful when. Okay, so this was our effort throughout this Tulu project, which started from 2023. And now we have an open, reproducible, and state-of-the-art post-training recipe. And we can apply it on many different open weight models. Okay. In the first version, which we worked on this on June 2023, we pretty much only showed what is the best recipe to develop supervised fine-tuning data or instruction data. I'm going to dig into all these a little bit deeper in the next slides. In the second version, we showed that how we bring and digest a preference data. And then finally, we started doing very systematic study on what are the best algorithms to use these type of preference tuning data. And at the end of these stages, we managed to show that with only open source models, we can be as good as ChatGPT, even upsetting GPT-4. Finally, at the end of last year in November, we released Tulu 3, which pretty much put all our efforts together such that we developed Tulu 3. Okay, and then we applied the same recipe on Olmo, showing that the fully open training recipe also works. Okay, so what is this training recipe? So it starts from a base model, and we are following 3 important steps: instruction tuning, preference tuning, and our new novel method, we call it reinforcement learning with verifiable rewards. Okay, and sometimes we have to do a bunch of kind of back and forth between these stages, and I'm going to talk about how this works. Okay, so let's first start getting the ingredients to start with, which is data. Okay, so in order to do a successful post-training, we first need to establish meaningful evaluations for targeted skills. For example, for Tulu 3, these were our goal. We want to have general chat capabilities. We want our model to be able to be good at knowledge recall, math and reasoning, coding, safety and non-compliance, multilingual, and also very precisely follow instructions, even when it kind of shows some constraints. Okay, so we developed all these kind of evaluation benchmarks. Like we decided what type of evaluation data sets. Sometimes we also had to create the data sets ourselves on how to evaluate if our model has acquired good capabilities in all of these categories that I just talked about. Okay, and we also followed really good old machine learning techniques, which we set some of these data sets for development, and then kept some as hidden, and we just evaluated at the end of when all our training was done. Okay, so given our emphasis on these capabilities, we started collecting prompts, like kind of queries and instructions that we think our model should be able to answer. Okay, we checked for licenses. Are they kind of collected with a user consent, how the licensing work, and then make sure that we decontaminate them with the evaluation sets that we are evaluating on. This is very important because we've noticed in the literature, people show some really good data sets, getting really good results on certain benchmarks, but the decontamination wasn't done carefully because we are talking about very complex instances, and it's very easy for some of the test sets to be contaminated. So we, in our Open Instruct toolkit, we have a code available for all these cases, and it's really useful to follow this. Okay, so now that we have the ingredients, we want to go through the first step, which is instruction tuning, or sometimes called supervised fine-tuning. What does that mean? It basically is a very simple step. It takes a lot of these prompts and completions, and then fine-tune a pre-trained language model to be able to follow these instructions, right? So for example, we can have queries like answer these questions one by one, summarize this document, like many of these type of questions, and then the final answers. Okay, but how do we curate this data? How do we source this data? We can have and source this data through human annotation, which obviously it is costly, it is time consuming, and also it has high variance, right? Now, sometimes, particularly in tasks like reasoning, we are dealing with complex annotations, and it might not be well suited for kind of general annotators. Another approach which we introduced in our 2023 self-instruct paper was to synthetically generate these data with kind of self-loop or self-instruction loop with another language model. Okay, so kind of synthetic data generation. And obviously it is good, it's really good in a lot of cases, but it's going to be noisy as well. Okay, and it is biased to the language model that we are generating this data from. Okay, and most recently we've discovered the optimal solution is combining both of them, which we kind of build a hybrid collection of data coming from human annotation and also from synthetically generated by other language models. Okay, so data curation has been kind of received well within the open source community. We had some earlier work in 2022 on, we called it natural instructions and supernatural instructions, where we only focused on kind of NLP relevant tasks, where we were looking at tasks like question answering, summarization, translation, and so on. Then we developed a self-instruct, a framework where we generate data synthetically. This has picked up really well within the community. Many kind of next efforts have been introduced within the community to generate more and more synthetic data sets like Alpaca, Vicuna, and so on and so forth. We also have a very good collection of data sets that are mostly focused on kind of short form question answering type tasks like FLAN V1 and so on. So I'm just listing a few of these data sets here. For the full set, please check our Tulu 3 paper. We listed a lot of publicly available data sets, either manually curated, expert curated, or synthetically generated by the community. And we kind of combine a lot of them, use the ones that we saw most signal out of them to build our final SFD mix. Okay, so now we have looked at all these kind of data that are available. And now we are doing these two repeated parallelizable tracks where we collect this data, and now we want to mix them such that we get high accuracy in the capabilities that we care about. This requires substantial effort. Why? Because, for example, if I add a lot of data about poem generation, probably my math reasoning capabilities drop. If I add a lot of data on math reasoning, probably I would lose this kind of creative task like poem generation, right? So it's a pretty challenging task to keep a good balance of all these data such that we are getting high accuracy across the board. Okay, so we are exploring, and also in the community, people are exploring many different ways of this data mixing, including manual kind of empirical analysis, automated mixing, and I think the literature is evolving, and there are a lot of active research going on in this area. Okay, so let me show you some of our efforts in how we did this data mixing in our Tulu one, which was kind of very simple. There were not much data available in 2023 such that we kind of start doing all this combination. So first we combined all available open data sets that were available back then, okay? And I'm listing them on the left. And some of them are created by humans, general public, or experts. And then some are synthesized with some of the most successful language models back then. Okay. Then, similar to what I just described, we started kind of looking at evaluation sets or data sets targeted to evaluate certain capabilities. For example, this is the outcome of our fine-tuning when we were evaluating on kind of chat type evaluation sets. Okay. And here are how the results compare. The red ones mean like the results are not that good. And then the blue ones show, okay, successful results. Like as you see here, that GPT-4 Alpaca shows good high results on chat type evaluation. Share GPT also showing good results on chat evaluation. So we did that across many different kind of verticals: knowledge, reasoning, coding, multilinguality, and safety. And some of these results are quite exciting. Like, for example, when we train with chain of thought data, we see higher numbers on reasoning type evaluation sets. Okay. So now the question is, how do we combine them? How do we take the best of all of these worlds? Because as you saw, this data, actually, let me go back here. this data, like share GPT or self-instruct, or like I would say Open Assistant 1, that is good in chat, they are not that good in knowledge or reasoning type tests, right? So it is important to kind of get the best of all these worlds. So we try to look at the data sets that show kind of high numbers across one of these verticals and started combining them. And as a result, we have a human plus synthetic type data. Okay. I want to highlight that we saw really good results with Share GPT early on, but we later dropped this data because license and the way the data was collected was not that good. So we dropped this data in our next versions. Okay. Now, with the emphasis on reasoning, I want to dig a little bit deeper on what type of data particularly is useful for reasoning. Okay, why is this challenging? Let me give you a math example. We want to solve this problem. The question is, you can read this here. A store has buy two, get one free deal on shirts. Each shirt costs $25. If Sarah wants to buy 7 shirts, how much will she spend? Okay. So one quick thing could be, okay, I have this problem. The final answer is $125. It's pretty easy to come up with that number. Okay. However, if I just fine-tune a model with this kind of input-output setting, probably I won't get that much out of this training instance. Okay. So we all observe in the community that it's really better if we start integrating and using this type of chain of thought output, where we say we're going to break this down into, okay, step 1 does do this, step 2 do this, and then kind of break this down as if you're explaining it to a child, how to follow these steps to come up with that final number, $125. Okay. So to summarize, why do we think chain of thought data is helpful for reasoning? It's helping the model to handle complex, multi-step problems much easier. It also starts kind of revealing the model's reasoning process. Also, one thought is a lot of these models during pre-training have seen a lot of these type of chain of thought data. And then this kind of starts to boost them up, to boost this capability up of saying, okay, remember you knew how to think step by step, bring them up when you are looking at these more complex math reasoning problems. Also, when we look at these type of annotations, these type of chain of thought data makes it much easier to spot errors in the logic. And also, it kind of resembles how we are explaining things to humans, or how humans' thought process work. Okay, these are all very good points about why this type of chain of thought data is important. However, it's becoming more and more challenging to observe and obtain manual annotation for this type of chain of thought data. It is time consuming, it is very expensive, right? And it often requires expert annotations. The example that I showed in the last slide was quite easy, but think of more challenging math problems. We need experts to annotate those. And obviously, it is difficult to scale. And also, it is not diverse enough. Like, it is very hard to boost diversity with all these kind of limitations that we have when we want to collect this type of chain of thought data. Okay. So again, our approach to address this solution was hybrid data curation, where we look at data mixing and also selecting from existing resources. We also did some very kind of observed a very interesting paper from the literature where they proposed to use different personas to generate diverse data. Okay, so I'm referring to this paper here, but the idea is we're gonna look at different skills, like for example, math, coding, precisely follow instruction, but then we devise different personas, and then we ask the model to generate data for those skills given the persona that it is kind of looking at. This would ensure high diversity and enables us to scale further. What does that mean? So we kind of develop this prompt. We say we want to create this data with this specific persona in mind. Like, for example, we want to create a math problem, given that we are creating it for a chemical kinetics researcher. Okay, and now the problem looks like this. Dr. Smith, a chemist, is studying this, and so on. Or we say we want to solve this logical reasoning problem, again, for that persona, for that chemical kinetics researcher. We tried many different personas, right? We designed these type of math problems for experts, for children, like 6-year-old children, or like a computer scientist, a musician, right? So you give many different personas to the model, and then we ask the model to generate it specifically designed for that persona. With that, we created more than 150K hard math problems and 50K grade school math problem. Okay, we created 35K Python coding and precise instruction following. Then these were mostly for generating prompts, because this was the point of boosting diversity for the types of problems that we are getting. Then we used a combination of GPT-4o and Claude Sonnet to generate step-by-step solutions, for example, for a given math problem, a coding, or precise instruction following. Okay, so now let's look at the results, how successful and useful these data are. Okay, so let me walk through how we read these figures. So in the figures below, you are seeing results on two data sets, math and GSM-8K, which are two popular math data sets. Then each of these bars show a combination of using our public data sets, like the data sets that are available, for example, for math or general purpose, combined with these persona-driven synthetic math problems. Okay, and we kind of varied the amount of these persona-driven math data in our experiments. Okay, so the first bar, the yellow bar, just uses the general public data, and the last bar is kind of does a 50-50 between persona-driven data and then general data. Okay, and as you see, over time, we see improvement, mostly on the math. On GSM-8K, we saw less improvement, and we think the reason is because GSM-8K are simpler math word problems, like grade school math word problems, and we think the available public data set were already good enough. So that's why we didn't gain much. Okay, so to summarize, adding more persona-driven data consistently improves math performance. GSM-8K improves, but it's much less, and kind of we kept a balance on how to use this type of persona. Okay, so we did another step to kind of filter the data. How did we do that? For every word problem or every kind of instance that was generated synthetically, we actually went ahead and asked GPT-4 to generate multiple reasoning paths. And then we basically did self-consistency. So in one of the classes earlier, I think this semester or last semester, you learned about self-consistency, and here is what we used. And then we basically saw which one has majority vote and kept those reasoning paths that gave us that kind of a better answer. So through this, we managed to filter a lot of data, almost 40% of the data. And now we are seeing that using only 60% of the data, we are getting similar performance on math, right? This new pink is the filtered kind of processed data, which is almost on par. I would say this is just kind of error bar on how different they are from the original mix. And we saw more significant boost on the GSM-8K, kind of highlighting that with this better filtered data, we are getting higher accuracy on GSM-8K. So at the end of the day, now we are able to use this 60% of the data, and we are getting good performance from this synthetically generated data. Okay. So there are many other approaches in the research community to generate chain of thought data. One is obviously manual human annotation. As I mentioned, this is great. This is very accurate, but we can pretty much have a limited scale. And sometimes it is hard to increase diversity in the reasoning scale, in the reasoning style. There are methods that they convert math problems into Python code and then generate solutions that way. This is great because it guarantees correctness through execution. It is the only issue is it's a little bit less natural, like natural language reasoning, the same way that you are explaining it to a child. So somewhat less intuitive, but it's still very interesting, and it works really well. And also this type of self-generated chain of thought, which is scalable to many problems. The quality of the model really depends on the base model. And we kind of did a combination of all of these methods. Okay. So putting all these together, so I talked a lot about how we created and curated these synthetic data for math and reasoning. Then we put all of these together and built our data mix for supervised fine-tuning, and this is the outcome, which is the combination of human and synthetic data, and we finally built Tulu SFD. So let's discuss a little bit of results. So this table has a lot of numbers, but I want to show kind of some of the ablations we've done. The columns show many different data sets that we evaluated on, like MMLU, TQA, PopQA, and they are all kind of evaluating some of those core skills that we cared about. And this is our final results on the final SFD mix that we discovered. And these are some of the ablations. Like, for example, if we remove wild chat, which is kind of our data mix, to approach general chat capabilities, our average will get into 58.9, with probably the biggest drop on, as you see here, Alpaca eval on chat evaluations. Or without the persona data, we get to 58.6, where we saw drops on, for example, math and so on. Okay, or math data, if we remove that, we see a really significant drop on this type of math evaluation. Another thing that we were very careful was we want to make sure our model is safe. So we added safety data, but at the same time, we want to make sure that it doesn't drop the capabilities, the general capabilities of the model. And this is what we've observed, that adding safety data doesn't hurt general capabilities of the model. This is also comparing the Tulu SFD data with the other data sets that were available in the community, like Mammoth data or RLHF. These were some of the most popular data sets that exist in the community. And this is like the gains that we are having, like 46, 56. And these were our earlier, like Tulu 2 SFD is like our earliest data mix in our earlier versions. So in overall, we argue that this is a really good SFD mix. A lot more can be done here. And it's really good if like people in the open source community also start improving this data mix. Okay, so step one is done. We took our base model and then did supervised fine-tuning with a very carefully curated data mix. Okay, next step is preference tuning, where it works with a reward model. Okay, let's see what happens here. So at the preference fine-tuning stage, I think Jason also talked about this, is the goal is we want to align to human preferences. For example, we have this query, we say, write a haiku about AI. It talks about the model comes and outputs something. We want to give thumbs up, thumbs down if the output seems good or bad. Okay. So, but in practice, what we've observed, the role of preference fine-tuning is to show a very strong training signal to make a style, to have a better style of chats, and it shows really higher improvements on chat type evaluation. It also keeps improving the basic capabilities that we were targeting, but in general, we saw lower absolute magnitude of improvement for like very kind of for example, math type capabilities. Okay. So let's dig a little bit deeper how the preference data looks like. So we have this prompt, let's say explain the moon landing to a 6-year-old in a few sentences. We want our model to generate 2 responses, okay? And then the preference instant tells us one response is better than the other one, right? And it can be annotated by humans saying that this response to me seems much more suitable for a 6-year-old. Most recently, people look at this called RLAIF, where instead of humans, we can have another AI model, let's say GPT-4 or Claude Sonnet or so, to evaluate which of these responses are better for a 6-year-old. And then the algorithm to kind of update that at some level, sometimes it's called RLAIF. Okay, so but this is the nature of data. Why does this data play an important role in kind of building and post-training stages is in a lot of cases, we are dealing with open-ended generations and kind of coming up with some absolute numbers to say, oh, okay, this response is good, is hard. However, it's much easier to deal with comparison, to say this response is generally better than the other one. So the task of annotation has become much easier, okay? But then we cannot use the same supervised fine-tuning algorithm to deal with this type of preference data. Now, let me unpack RLHF or reinforcement learning with human feedback. How do we integrate and use this type of preference data? Okay, so we will use reinforcement learning. How does it work? This is the most generic form, okay? The idea is, this is kind of the most generic definition of RL. The idea is for a given policy, which is generate the next token, we generate this next token, we interact with an environment, we get some reward from the environment if that generated token was good or bad, and then update the state of the world. In RLHF, the state is getting updated from the prompts that are getting fed into the policy. The action is updating and finding what responses are. And then the environment is actually a reward model where it tells us how good a model like kind of tries to model the preferences that this response is generally preferred over the other one. Okay, so this is kind of how RLHF works. These preference data will feed into a reward model, where reward model is actually a neural network that is trained to tell us for a given prompt which response is better. Okay. How do we optimize this complex situation? Through PPO training. Let's dig a little bit deeper. The idea is we want to maximize the reward, we want to get the maximal reward as possible, okay? Such that we want to constrain the model to stay as close as possible to the base language model, right? Like we want the policy to don't go that far from the originally trained model. Okay, so this is establishing a very important balance between make sure you are aligned with those preferences that are provided to you. However, don't go too far from the original model that you have in mind. Okay. Now, in the last year or so, many different variants are introduced on how to optimize that objective. Okay, so in last year, we had this paper called Direct Preference Optimization, or DPO, where the idea is, what if we just use gradient ascent on this equation? Okay, let's kind of ignore all that. Like now we have this reward model, and then we want to optimize for that reward. Let's directly optimize for these human preferences, and then kind of model it as a ranking model. Okay. So how does the DPO training work? It's like this, where we kind of remove a lot of these details here, and we directly go from the preference data into policy. And then kind of given that reference model, we want to see how close this preference data is to the policy. So many new variants of DPO also introduced. So here I'm summarizing them. This is the PPO, the original formulation. Here is the direct preference optimization, which directly optimizes the policy given the preference data. I would always say, think of it as kind of some sort of ranking objective. And then the newer variants like SimPO, which even makes it more simplified, where it doesn't even use a preference, a reference model. Another variant like length normalized DPO, which normalizes the same likelihood, but kind of make it normalized for the length. Okay, so in our this work, we started actually digging deeper into all these algorithms that exist. Okay, particularly we looked at comparing between DPO and PPO. Okay, so they are all different, right? They are getting different types of parameters. They have different implementation complexity, memory usage, throughput, and so on. Just to give you a very brief idea, in general, we saw PPO performs better than DPO in almost all cases. However, it is much more complicated to implement and make it work, particularly for larger models. Why? Because for PPO, we need to have two models running. Like we have the reward model as a neural network, and also the policy model, which is kind of the actual language model that generates token. Okay, so it really depends on the developer's preference on which constraints they have. Okay, so let me dig a little bit deeper and tell you what things we ablated to figure out which model to use. Okay, for DPO, remember we had preference data and policy model. For PPO, we have all these components: preference data, the type of reward model, and the neural network that we have here. We have the generations, the prompts, and the policy model. Okay, so I'm kind of showing the final results. I'm not going into a lot of details, but here are the results. Let's say this is the average performance on a lot of tasks that we've looked at. This is the initial SFD result. When we do DPO with some sort of weaker preference tuning, we saw 2% boost. Okay. When we do a lot of ablations and very careful curation of preference data, we saw significant boost. Like, look at this. We go from 56 to 61, just with better data selection and data curation here. Then we replaced DPO with PPO. We saw now we just use the exact same data. We just replaced the algorithm, DPO with PPO, and we saw 1-point boost here. Then we thought, okay, now this is very promising. PPO is great. Let's now think of a big reward model, because remember, reward model plays this environment role, and we kind of try to make our model as close as possible to this kind of preference data. Okay. When we started using a bigger reward model, we didn't saw that much improvement, like less than, like about 0.5 point improvement. And then finally, when we started mixing prompts of what type of specific design prompts for some tasks, on average, we didn't see much gain. Okay. However, I want to highlight that this final step on average didn't show us a lot of improvement. But very interestingly, when we only focused on reasoning, particularly GSM-8K, when we started bringing up prompts that are very useful, like for improving the reasoning capabilities, we saw significant boosts here. That here we learned when we introduce prompts that are domain specific, for some of those capabilities, they play a really important role. Okay, so if you look at this whole thing, this was the choice of algorithm, this was the choice of data, algorithm, model, data. So again, we saw a really big boost on data. Okay, so takeaways from this. The most important factor in building a really good preference tuning algorithm for us was high quality data. PPO works better than DPO, but DPO is much cheaper to experiment with and kind of do ablations on data. And it's kind of more practical for development. Scaling RM reward models help, but not significantly. Using end-domain prompts yield performance gains, particularly for domains like reasoning. Okay, so now we put all of those together when we want to build Tulu 3. Okay, so from our last study, we learned prompt selection is really important. So we looked at many different combinations on how to curate data, and this was kind of our best mix. We want to use some of the prompts that we already use in SFT. We thought this is really good to maintain accuracy and performance. We also brought some prompts, some new prompts that we hadn't seen during SFT. And then we started bringing in out-of-domain prompts, for example, from domains that we did not study in SFT. Okay, so we then did a lot of response generation from all these models. Okay, so we had some weaker models like 7B models, Llama 7B, for example, Almost 7B, all the way to very kind of strong models like GPT-4o, because we want to look at the preferences to see which of these outputs are more preferable. Importantly, we brought on policy data. Remember, we want to improve our Tulu 3 SFT, right? This is the model, this is the policy model that we want to improve upon. So we made sure to bring some of these data points and these Tulu 3 completions such that we can say this outcome is preferred over something worse, or we need to get to something better, which is, for example, the outcome of GPT-4. So we also show that it is important to use this on policy data. Okay. Then we did particularly RLAIF, where we asked GPT-4o to tell us which of these completions are better. And we ask it to measure across these 4 categories: helpfulness, instruction following, how accurately it could follow instructions, how truthful and how honest these responses are. And then we binarize them according to and then said which is chosen, which is rejected. To optimize the algorithm for optimization, we did a DPO, PPO, and SymPO. Again, similarly, we didn't see much gains from PPO, and for simplicity, we stick with DPO for this. Okay, so here are these bottom figures, show some of our ablations. So actually, let's look at the right-hand one, which is what LLM as judge we used for kind of telling us which is preferred, which is rejected. And we looked at many different kind of highly capable models like GPT-4o, Llama 405, and so on. And we saw a little bit better results on GPT-4o, and that's what we stick with. This middle figure evaluates the off-policy versus on-policy preferences. And as you see, this is the initial SFT. With off-policy, we got to 60. Adding on-policy, only with on-policy, we get 60.7. And then combining all of them, we got the best numbers. Here, we also checked if it is useful to bring in new out-of-domain prompts, or we just reuse some of the prompts that we had from the initial SFT. And as you see, again, bringing new prompts also improves results. Okay, so what happened up to here? We did all our instruction tuning, supervised fine-tuning. We did our preference tuning. And now I want to talk about our third step, which we introduced as part of our Tulu 3 effort, reinforcement learning with verifiable reward. Okay, so let's look at these curves. At the end of DPO or preference tuning stage, I'm going to show you these three figures. Okay, so this is training steps on the x-axis, and on the y-axis we are looking at evaluation performance. And as you see over time, for example, in the alpaca eval, we see the improvements are almost getting plateaued. Okay. For if eval, which is how we do instruction following, interestingly, we see when we increase the training steps in the for our DPO, we see a little bit drop in performance. And for GSM-8K, which is our kind of proxy for reasoning, we see initial improvement, but then after some time, we started seeing overfitting and then dropping performance. Okay, so particularly for these more complex tasks like following instructions and doing reasoning, over time, we see over-optimization is happening, okay, which is not good. Then we started thinking a little bit about this. We are using this neural reward model to tell us if kind of some preferences are good or bad. Okay. This neural network tries to assign a score to every instance now. Okay, so it tells us for this reward model is trained to tell which is chosen, which is rejected. But at the end of the day, for every completion, it tells us what is the score of this completion. Okay, for example, for something like this, for some prompt like this, it would give us this score of 10.5. Okay. If we change the input, it might give us another score. Okay. Also, there are studies in the literature that this human feedback that, okay, this A is preferred over B, it's not the gold standard of saying what is the outcome, what is a good reward score for this sentence, for example. Okay. Instead, we thought for tasks that we can verify their correctness, we can use a much simpler reward model. Okay, or in fact, we can replace this reward model with something rule-based. For example, if my query is what is 2 plus 2, we can easily say if the answer is gold, return 1, otherwise return 0. Okay, if we were only using that neural reward model, it might have given us another score like 1000, or it might have given us something like, I don't know, 5.5, right? What is the intuition, or what is the meaning behind that score that the reward model is giving us? Okay, so that was where we questioned this. And then we said for tasks that we can verify their final outcome, what if we just remove that complex setup and use a much simpler rule-based model? Okay, and this is exactly what we did. So let's look at our RL setting. The prompts come in, the state gets updated, the action are generating next tokens, and then this reward model tells us what is the good outcome or what is a good score associated with this generation. However, in problems like math that we have ground truth answer, we can have this verification function where the reward tells us 1 if the final answer is correct, 0 otherwise. Okay. Pretty much we had that for GSM-8K, which is one of our reasoning evals, math, and also precise instruction following. Let's imagine we are giving the model a bunch of constraints, like make sure to start the sentence with S, then or to write a poem that has 5 words, right? So you could verify if the generated outcome follows these constraints or not. And then we can kind of evaluate how we can easily verify how good the generated outcome is. Okay, so that was pretty much what we did. We replaced the reward model with the verification function. And this, the DeepSeek R1 model that released earlier this year also is using similar thing, which I think they call it a different name, but a very, very similar intuitions. Okay. To summarize, this is our setup. We use goal final answer or verifiable constraints as this kind of environment, as a proxy for environment. This is good because for this, we don't need intermediate chain of thought. We just need the final answers. Then we applied classical reinforcement learning algorithm to optimize this. And here we used PPO for the optimization. And we tried it for 3 data sets, GSM-8K, math, and if verification, and kind of we show the results. Roughly, this is the number of training instances that we have used, almost in the order of 100, 110K. We also evaluated on Big Bench Hard, which is kind of also roughly reasoning type task. And then we found that this FLAN dataset could be a good proxy to give us boosts on BPH. Some of the verification steps are very easy, like math and reasoning. It's pretty much just this if then else, which is if prediction is equal to this number, say yes, otherwise 0. Some of it, for example, for constraints and constraint satisfaction and verifications, it's a little bit more challenging because we want to see which of these constraints are satisfied, and then we see which percentage of those constraints are satisfied. But in general, pretty similar, pretty easy. So now let's look at the curves. So I'm just showing this whole graph, but now let me go a little bit deeper here. Okay, so what does this curve tell us? So on the x-axis, we see the training steps, and on the y-axis, we show the GSM-8K, the math reasoning capability. This dashed green line is the outcome of the supervised fine-tuning model. The pink one is the outcome of the DPO model. Okay, so we applied RLVR at 2 stages just to see if it makes improvement, both at the end of supervised fine-tuning and also at the end of DPO. So what do we see? This is interesting. Curves show results are going up. We don't see that much over parameter optimization here. The gains on top of SFD is much higher, but the biggest gain, or like the highest number, is achieved by when we apply it on DPO. Same things on math. Again, at the beginning, we saw a little bit drop when we started with DPO, but then again, start to see improvements. If eval, which is the verification on the constraint optimization and like instruction following, when we start from SFD, we saw significant gains. On DPO, we saw less gains. We are still investigating on this, but we think the reason is we did not have enough data. And interestingly, when we used FLAN data, just to see, this was kind of, we did not finally include this in our RLVR mix, but it was an interesting observation just to see that doing some reinforcement learning on FLAN, it shows some improvements on some of the reasoning tasks. And it's worth exploring this much more. And we are doing it, just seeing what other types of verifiable tasks out there, such that we can apply RLVR on that. Okay. We also applied the same recipe on Olmo 2, and we can kind of build upon this. This is actually a very interesting setting. We stacked a bunch of reinforcement learning steps, one on top of each other. So here we started doing a bunch of training, and we kind of cut it here. This is the average score. And then again, started a little bit, and another step. And then I kind of stacked multiple RLVRs and then did multiple stages. And over time, we saw even more improvements. So the pipeline is there. We can do multiple kind of tries with this to see if we see bigger gains or not. Okay, I want to take a step back and then talk about this thing. RLVR is not really new. This is actually the simplest way of using RL with kind of data. But why did it work now? We realize it's because now, base model qualities have improved a lot. Therefore, RL can boost upon them. Okay, so what does this curve show me? So these are training steps. This is the accuracy. And the green bar shows when we do RLVR applying on GPT-2, like the model that existed long time ago, which was really bad. So the original number, like the base numbers are very low, unlike some of these reasoning tasks. Therefore, reinforcement learning didn't show improvements. However, because now our base models are improving, then applying RLVR on top of them shows significant gains. And this is very interesting to observe because now model can start exploring more and then exploit it once it sees it is following with the reward, with this rule-based reward. Okay, so putting all these together, we scale this up from 7B to 70B to 405B. And this is kind of our results, how it looks. On the pink portion, you see the results of the Tulu model applied on Llama 405B. Here are the results of SFT, DPO, and the final out of RLVR. Again, this is the result comparing with DeepSeek V3 and GPT-4o, the latest version. On average, we are very close to GPT-4o, better than DeepSeek V3. And it's a very exciting area. Here are showing our results on 8B and 70B models, again comparing with open weight models like Qwen Instruct and Llama Instruct, which like better significantly, and also at 70B, where the smaller model are also comparable to the kind of a smaller size of GPT-4o Mini or Claude Haiku. Okay. One other interesting observation was RLVR works better at the scale. So here shows our improvement on math in 2 cases. Oh, I didn't put legend. So here on the left-hand side, you see how much improvement we see on a 70B model. And this is how much improvement we saw on the right-hand side. You see how much improvement we saw at 405B. And as you see here, we started from 60, went all the way to 67, like 7-point improvement on math. Whereas at the 70B scale, we go from 42 to 45. So it was interesting and kind of aligned with our hypothesis that when we have better base, we can start seeing a lot more improvement during this RLVR step. So we are exploring a lot, and we know the community is also exploring a lot in this setup. For example, we have changed our optimization algorithm from PPO to GRPO, which I'm not going to go into the details, but now here are our significant improvements. So as a reference, Tulu 3405B has 67%. And now when we apply our recipe on Qwen math model, and then we apply GRPO, now we are already getting 84.6. So which is very exciting, shows a lot of progress can be done in this domain. Okay, so this is it. So these are putting together all our Tulu 3 recipe. I first talked about how we got ingredients ready by collecting data. Then we have different types of data at different stages, and we showed how we do supervised fine-tuning or instruction fine-tuning, preference tuning, which we looked at the preference data, and RLVR, which we just looked at this kind of verification step. And then putting all these together, we have Tulu 3. Here is the model. We also have the demo of the model available in playground.lnai.org, where you can play with this. We are using this data to kind of improve the next version of the models and kind of improve capabilities of Tulu 3. Also, all our code data and the pipeline and the framework is ready. So whatever post-trained model or adapted model you want to build, we argue it's really important to bring in some of the general capabilities to get better model. So I would encourage you to use that data. Okay, so this is a fully open post-training recipe. We have applied it to Llama-based model, Qwen-based model, and also on our Olmo models, which shows significant boosts on the kind of Olmo-based models as well. Okay. So with that, I would end my discussions on post-training, and I want to very briefly talk about test time inference, okay, which is a very kind of popular topic these days, and a lot of people are looking at how to bring in test improvements, particularly in reasoning during test time inference. So I first want to talk about this paper called Swan, which is led by amazing Nicholas Menninkoff. And it is actually the very minimal recipe for reasoning and test time scaling. So let me tell you how it works. Very similar to almost everything else that is happening in language models, it relies on really carefully curated data. We call it S1K. Then we apply test time scaling algorithm, a very simple one, and this is the outcome S1. Okay, how do we curate data? We looked at a very large collection of math, logical reasoning, probability questions, and so on, like kind of more higher level reasoning data. It's even beyond the Tulu 3 data, where we mostly looked at grade school and kind of math, which was high school, a little bit college level math. Here we are looking at much more complex, like even Olympiad or math competition type data. So we looked at all these logic puzzles, math, and we collected 59K questions. But then we did a lot of filtering here. We filtered for quality. We got into 52K data. We picked the ones that were more difficult, and then we moved to 24K, and then we emphasized diversity, and we kind of removed the ones that they were very similar. We ended up having 1K. So spoiler alert, on our benchmarks using 59K data and 1K data, almost similar, which is very interesting. So once we collected these prompts, we started to distill reasoning traces and answers. So for example, when we have a problem like this, we gave this problem, which is among our like S1K data, and then we annotated the kind of reasoning chain of thoughts with Google Thinking Gemini model. Also, we made sure that this data also includes some of the thinking tokens, like, okay, this happens, but let me think more and so on. So we use the kind of Google Thinking annotations. And most recently in S11, we replaced Google Gemini result annotations with DeepSeek R1 results, where it actually improved the final results, which was very interesting to see. Okay, so this is the final collection of data. The data varies across all these domains, from geometry, number theory, to even very smaller portion on control theory, astronomy, and so on. Okay, so this is the data. Test time scaling, the simplest method possible, which kind of made all of us very surprised and kind of excited, where we focused on budget forcing, where we have a question like this: how many R's are in Raspberry? We let the model generate the response. But then if it didn't hit the allocated token budget, we added a token called weight, and then let the model generate and basically force the model generate more in order to respond to that, right? We are kind of using this weight token. We are hinting the model that we are not sure if your answer is correct, okay? So one more thing to add, we did not train a model to decide when to add weight. We kind of naturally added weight when it didn't hit our token budget. And then we let the model generate more until the final answer is achieved, is obtained. Okay, so now training and results. We trained a Qwen 32B model on this data, and here are our results. On the x-axis, we are seeing the kind of the number of tokens, the average thinking time, or the number of tokens that are generated, and then the accuracy. So when we push the model to just generate 512 tokens, here is the accuracy, right? It's like 65. One more thing, if the model wants to generate more tokens than the budget, we put end of token there, or end of a sentence there. Okay, so with that we control the generation. So we go from 512 to 2048 for math 500 data. And as you see, over time, with more generated tokens, we see this scaling trend. On this math competition data, which is kind of much more challenging data, we even want the model to generate longer and longer outcome. And as you see here, we see, again, the same trend, and also PhD level GPQA diamond, again, generating longer and longer tokens, which is very exciting. Okay. So zooming in, here are a little bit of how it works. I kind of explained it already. So when the model wants to generate more tokens, we pushed end of sentence to be able to get these kind of shorter sequences. And when we want the model to generate longer, like even go beyond 8,000 tokens, we push these away token and force the model to generate more. We compared different types of test time scaling methods. Here are the budget forcing. This kind of steeper curve shows the budget forcing or sequential scaling. We also did parallel scaling via majority voting, where we let the model generate multiple paths and then kind of do majority voting, or like the self-consistency check. And we saw some gains, but not that significant, right? So this kind of budget forcing seemed much more successful and much simpler. So here are some of these ablations that we have done in the model. So this is the final results on the left-hand side of S1K on all those three data sets. Comparing with full collection of data, like using 59K, we see that a little bit higher numbers we get with the full data on AIME, but in other cases, pretty much similar. And our S1K data is really high quality. If we just use random, or like just do a bunch of kind of constraints to find that 1,000 data points, the results are much, much worse. We also did a bunch of scaling ablations when we don't increase any kind of let the model to train longer. This is the base number. So these are the gains that we are having with this test time scaling. If we replace the weight with other tokens, like alternatively, or just let the model generate without adding any strings, we saw less gains. Okay. So these are our results for test time scaling. I also want to highlight two other approaches that we have been cooking up over time. And the idea is, and I'm not going to talk about any details on these next two methods, but the idea is we want to be very aware and do self-guided generation at inference time. In this work, self-RAG, we build a RAG-based model, retrieval augmented generation model. But in this setting, we train the language model to generate tokens, but then criticize its outcomes and self-improve. And we did it the whole loop with generating these critic tokens, where the model generates responses, but once in a while, it generates tokens to say if the generated response makes sense or not, or if the retrieved documents make sense or not. So these are also very promising directions in pushing for test time scaling. We also showed that how this kind of self-guided improvement loop helps in synthesizing scientific literature and answering very complex questions about scientific tasks that require lots and lots of reasoning. So please check out these two papers. The results are very interesting. We also have a demo, which is openscholar.ln.ai, where you can play with this system, type your question, and then see how it can answer and combine different pieces of information, synthesize knowledge, and then answer queries for this type of task. Okay. This is a demo, and I would let you play with it. So I want to very briefly also talk about how reasoning can get integrated during pre-training. Okay, so far what I talked about was post-training, integrating things at inference time, and now let's kind of go backward and then see how these things can be added during training. Remember when I said RLVR didn't work when we had weaker base models. So we need to push to have stronger and stronger base models. Okay. So this is kind of a, when we say training base model, it's not just training with the next token prediction where learning rate stays the same and so on. We usually do multiple stages of training. In this first stage, we have the warm-up period, which is a very standard method. But then we use cosine learning rate to train these models with the next token prediction on trillions of tokens. Okay. But then toward the end of training, we curate really, really high quality data, in a lot of cases designed to do more complex reasoning. And then we take the model that is here, the learning rate that is here, and then kind of anneal it to zero. So sometimes this stage is called mid-training. The role of these 50 billion tokens is very important because we still do next token prediction, but these tokens are very kind of are trying to focus on very complex tasks and emphasize on more reasoning oriented setting. Okay. And roughly this is called nowadays pre-training and then mid-training. So the pre-training stage, it uses most of the budget in the training stage. It uses trillions of tokens. It's pretty much unstructured, diverse text. Lots of it comes from web data. And we try to use the best type of data that we could collect given the compute budget that we have. During mid-training, it's almost 1% of training. The idea is we're going to upsample high quality data that we have during pre-training, and then to make sure that we have some in-domain data. But then we make sure to bring some even supervised fine-tuning data. We bring in a lot of reasoning type data, coding data, and we kind of try to emphasize the quality of the data here. Okay. So this is, for example, the pre-training data mix that we use for ALMA 2, which are some of the web pages, some code data. I mean, the leftmost column matters less. The rightmost, the categories make more sense to follow right now. Our web pages, code data, academic papers, STEM papers, some math web pages, and math proof, and so on. And in total, we have roughly 4 trillion tokens. But then during mid-training stage, we started to bring in lots and lots of math data, which started to patch the math reasoning capabilities that the model didn't originally have. For example, this was very interesting observation. We realized at the end of this stage, the Olmo model was not that good in doing multiplication, but much better in doing addition and subtraction. So we started integrating some synthetic multiplication data in the mid-training state, right? So you kind of observe, do a lot of kind of evaluations, and then figure out, do some patching to improve the model, and then kind of inject that type of knowledge in the model. So as you see in our mid-training mix, we included a lot of reasoning type data. And then we started evaluating these models. So this is kind of evaluating our pre-training and and mid-training together. On average, we see significant boost in both settings. Like from 50, we go to 60. From 56, we go to 68. And the biggest gains are on GSM-8K, which is our math reasoning capabilities, and DROP, which is also question answering with math data, which is showing significant boosts there, which is very interesting. Okay. So putting all these together, here are our Olmo 2 results, which is on par with Llama 3 8B. Please refer to the paper to look at the kind of the 13B, and most recently, we're going to have a 32B results. Okay, so with that, and I want to finish this, that we've seen a lot of progress in today's AI work. Still, we need a lot of research and innovation in many newer tasks. So here I've listed a lot of them relevant to reasoning, agents, language models for other domains, and so on, which I really would be excited if I see you work on that. With that, I want to thank a lot of people who are in my team in the Olmo and Tulu projects, and also my students at UW, and a lot of people at AI2. So thank you very much. Also, if you are interested, we are hiring for all these projects. Thank you.